So let's go ahead and see what we can learn about the derivative, the concept of the derivative, and kind of what it really means. So I draw out this arbitrary function over here, f of x, and I've indicated 2 points. So we have this x value, x over here, and we have this other x value, which is x plus h. So h is just some real number, it's some positive real number that's just slightly above x. And we know that the corresponding f of x values are just going to be f of x and f of x plus h as a result. We don't really care what this function is, we just know that we have these 2 points and their corresponding f of x values. And so what we can do is we know that we can calculate the kind of secant line between these 2 points. So what does that mean? Is if we take some line and we connect these 2 points in this manner over here, then we have what we call a secant line. I'm going to remove that. We have what we call a secant line. So this is what we call a secant. Sometimes you'll see secant line or just secant. And if you remember from geometry, a secant line on a circle, like if you have a circle, then a secant line is just a line that intersects that circle at 2 different points, but then never intersects it again. And it's the same exact concept for this graph over here. We know that the secant line, it intersects the graph at f of x and f of x plus h, or if you want to think about the x values, it intersects it at x and x plus h. And we know that we can calculate the slope of this line, so I'm hoping we all remember that the slope is just going to be the change in y divided by the change in x. And we know what is the change in y. So our final y value is f of x plus h, right? So it's going to be f of x plus h. And we're going to subtract from that the initial y value, which is f of x. And then what we can go ahead and do is divide that by our change. Why does that look so weird? We're going to go ahead and divide that by our change in x, which is going to be our final x value, which is x plus h right over here. And our initial x values, we're going to subtract that, which is just going to be x. And we can notice that x and negative x over here, these two cancel out, so I'm just going to go ahead and erase them. And so right over here, we have an equation for the slope of the secant line. So this is the slope of this line right over here. So this is the slope. And the way that we can interpret the slope of a secant line between 2 points is kind of like the average rate of change. So average rate of change of our function between x and x plus h. So what does that mean? It means that this is kind of like the average slope of the graph. This is the average rate of change of the graph between these 2 points, between the point x and x plus h. And we know that the coordinates of these points are going to be x comma f of x. And then here it's going to be x plus h comma f of x plus h. Right? And so what we can do is we can figure out the slope of the secant line between these 2 points, and that gives us the average rate of change of the function between these 2 points, or the average slope of the function between these 2 points. But we can also do another thing, and I'm actually going to go ahead and pick another color. Whoa, what just happened? This is a nice purple color. Actually, orange. So what we can do is we can define what we call a tangent line. So what I'm going to do is I'm going to try to show you something. What happens as h gets small? What happens as h approaches 0? Essentially, as h approaches 0, we know that x plus h is just going to approach x, right? Because if h goes to 0, then we're just going to have x plus h. For example, if h is 0.000001, then that plus x is just going to be super close to x. And so what we can do is we can start, I'm going to try to illustrate this, we can just bring this x plus h even closer to x. So we can make it, for example, right over here. So this could be our new x plus h. And then, of course, it would have its corresponding f of x value. So that would be x plus h, comma, f of x plus h. And then we can make it even closer, right? We can bring this thing extremely close to the point x, right? We can bring x plus h very close to x by taking h to 0. So as h approaches 0, then x plus h approaches x. And so by definition, what does that necessarily mean? So eventually these things are going to overlap. They're going to converge to this one point right over here. This is when h equals 0. When h equals 0, then we're going to converge to x. And as h approaches 0, we're getting extremely close to x. So the distance between x and x plus h starts getting closer to 0. And so the way that we can define the slope of this line as h goes to 0 is the limit as h approaches 0 of x plus h, or f of x plus h, minus f of x over h. This is basically just the slope of our secant line. However, we're just taking the distance between x and x plus h, and we're making that distance become extremely small. So we're that a distance between those 2 points is approaching 0, which is why we're taking the limit. And so then what happens as this limit approaches 0, as h approaches 0? Then our secant line that we had between these 2 points, because these are 2 distinct points over here, right? But then as h approaches 0, then x plus h is going to converge to x. And so then we can say that this secant line over here is going to converge into a tangent line. And so this is what we call a tangent line. So let me go ahead and label that. So it's a tangent line. And if you, again, remember from geometry, the tangent line of a circle is just some line that intersects the circle at one point. It kind of just scrapes the circle at one point, but then never intersects it again. And it's the same concept for a tangent line to a graph. And in fact, this right over here is what we refer to as the derivative. So we denote it by f prime of x. And this prime over here tells us that this is the first derivative, and we're going to come to find that we can take many derivatives in certain cases. So the number of kind of prime marks that you have indicates the numbers of derivatives you've taken. So this right over here is what we call the derivative. This is the derivative, and it's basically, the way you can think about it, it's the slope of the tangent line to the graph at a given point. So at our point x right over here, if x plus h converges to just x, then we're taking the slope of the tangent line. Or another way to think about it is that this is the instantaneous. So the instantaneous, I don't know how to spell that, rate of change of f at x. So essentially, this is the instantaneous slope. Like at this point x, what is the slope of the tangent line? What is the slope of our function at this point x? So what is the rate of change of our function at this point x? And that's what the derivative gives us. So this is the way that we can define the derivative. And if you want to think about it, if this is our change in x right over, or sorry, a change in y, and this is our change in x, then we can rewrite this to be equal to the limit as the change in x approaches 0 of the change in y over change in x. So another way we can interpret it is just what happens, how does our function change when we vary x an extremely small amount? And then this thing over here is going to be what we call dy over dx. And so this dx over here, this is what we call a differential. This is a differential. And essentially, it's a very small, I'm going to write that out, a very small change in x. And the same thing applies to y as well. These are both differentials, but this one would be a very small change in y. And so essentially, what the derivative is telling us, it's telling us when we change x an infinitely small amount, how does our function change as a result? So what is the rate of change of our function if we change x an extremely or an infinitely small amount? And so that is the way that we would interpret the derivative. So we have different notations. We have the kind of f prime of x notation. We have dy dx is what we call Leibniz notation. Leibniz, I think that's how you spell it. This is Leibniz notation. Another notation that you'll sometimes see is called Newton notation, where you'll have y with a dot, and the dot indicates kind of the number of derivatives. So this is like the Newtonian notation, but you don't really see this one very often. But the point is that I kind of just wanted to introduce to you the derivative as kind of the slope of this tangent line. It's very similar to the secant line, but the slope of the tangent line is essentially, the tangent line is the result of the 2 points of your secant line getting infinitely close together.